Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll take an introductory look at the Eaton EZ512 DCR Intelligent Relay, just one member of the Eaton EZ Intelligent Relay family. Our objective is to take an introductory look at a representative example of an inexpensive, basic, fixed programmable logic controller, in this case an Eaton EZ512 DCR Intelligent Relay. We'll familiarize ourselves with the device and learn how to program it using the ridiculously small LCD screen and dedicated buttons. Later lectures will make use of the much easier to use Eaton EasySoft software to program the device. This lecture is not intended to be a thorough review nor an endorsement of the EZ Intelligent Relay family, but rather serves to familiarize the viewer with just one of the many inexpensive basic fixed programmable logic controller options commercially available. Since we'll be examining specifications of the Eaton EZ512 DCR Intelligent Relay, it may help the viewer to download the datasheet and/or catalog entry for the Eaton EZ512 DCR Intelligent Relay. Go fetch and play along. The EZ Intelligent Relay product line is made up of three families: the EZ500, the EZ700, and EZ800. The EZ500 family is designed to control small applications with up to 12 input and output points. The EZ500 family is fixed and cannot be expanded. The EZ700 family is designed to control medium-sized applications with up to 20 input and output points. The EZ700 family is locally expandable up to 40 input and output points. Local, if you'll recall, means at the point of use. The EZ800 family is designed to control large-scale applications with up to 20 input and output points. The EZ800 family is also locally expandable with up to 40 input and output points. Additionally, the EZ800 family is remotely expandable using the proprietary EZNet network with up to 320 input and output points. Remote, if you recall, means over a network. All of these models on a DIN rail and are available with and without displays. Interpreting the part numbers of the Eaton EZ Intelligent Relay product line is astoundingly easy. 5 fields immediately identify important basic characteristics. The fields are as follows: module type, number of input and output points, supply voltage, and digital input requirements, output type, whether the module does or does not have a clock, and whether the module does or does not have a display. Note that not all combinations of fields are available. Using the legend, we can see that our representative example, the Eaton EZ512 DCR, is part of the EZ500 family, has 12 input and output points, 8 of which are inputs and 4 of which are outputs, operates on 24-volt DC, uses electromechanical relay outputs, does not feature a clock, and does have a display. Diving into the specifics about this particular model, inputs are designated I1 to I8 and are located on the top of the device. Electromechanical relay outputs are designated Q1 to Q4 and are located on the bottom of the device. Power connections appear in the upper left. This device is intended to function on 24-volt DC and necessitates an external 24-volt DC power supply. Now, inputs I1 through I6 are digital in nature. Recall that a digital signal is one that is characterized by a clear and definite transition between two mutually exclusive binary states that is never a little bit of both or halfway in between. Customarily, PLCs designate these mutually exclusive states as a logical 0, low or false, to be the absence of voltage, and the opposite as a logical 1, high or true, being the presence of full pilot voltage. Given this device operates on 24 volts DC, 0 volts is recognized as a logical 0, and 24 volts DC is recognized as a logical 1. To account for noise, the Eaton EZ512 DCR Intelligent Relay allows a range of acceptable zeros and ones. Any digital input receiving 0 up to 5 volts is assigned a logical 0 or false. Any digital input receiving above 15 to the full 24 volts is assigned a logical 1 or true. Digital inputs receiving continuously varying analog signals, signals between 5 and 15, or any signal in excess or of the opposite of the intended polarity are invalid. Digital inputs I1 to I6 could be used for switched input like push buttons, limit, and pressure switches. Inputs I7 and I8, in contrast, are analog in nature. Recall an analog signal is one characterized by a continuously variant magnitude inside a given range. The range for inputs I7 and I8 is 0 to 10 volts. Analog inputs I7 to I8 would be used for measurement devices like pressure and temperature sensors that not only detect a phenomenon, but also measure it. Sensors, or transducers, if you recall, output a voltage or current signal proportional to the magnitude of the measured quantity. Inputs I7 and I8 can also be used digitally, where an acceptable 0 is between 0 and 5 volts, and an acceptable logical 1 is between 8 and 10 volts. Used digitally, an invalid range exists between 5 and 8 volts. In the lower right, the device is a communication port that enables connection to a PC using a USB cable. The communication port allows a technician to program and monitor the device using the Eaton EasySoft programming software. There are 4 cursor buttons that allow navigation and 4 operation buttons: OK, Escape, Delete, and Alternate. We'll be making use of these dedicated buttons to write a program on the ridiculously small screen. Note if the device is set to start in the run mode and contains a valid program, upon power up, the device will immediately execute that program. This can be hazardous in an industrial environment, so familiarize yourself with the proper shutdown and startup procedures of whatever system you're working on. Let's assume that this is our sample system. Note the schematic indicates that there is a normally open maintain contact selector switch on input 1, a normally closed momentary contact red push button on input 2, a normally open momentary contact green push button on input 3, and a normally open momentary contact yellow push button on input 4. Digital inputs 5 through 6 have no field input devices attached, nor do analog inputs 7 and 8. Electromechanical relay outputs Q1 through Q4 selectively energize or de-energize pilot lights. Upon powering up the device, we see it immediately goes into run mode. Across the top of the LCD screen, the device indicates which of the inputs are activated. It looks like I2 is energized, as we'd expect given the normally closed electromechanical nature of the field input device attached to I2. Across the bottom Q output entry of the home screen indicates which of the outputs are activated. It looks like no outputs are energized. The OK button takes us to the main screen. We've got a couple choices: Program, Stop Run, Parameter, and Info. The blinking line indicates which option is currently selected. Note the checkmark on Run in the second line. One can view an existing program on a running device. However, one can only reprogram a stopped device. We can navigate to the Stop Run entry using the arrow keys and press OK. The checkmark indicates that the program is now stopped. We can now navigate to the Program entry using the arrow keys and press OK. In the Program menu, we're offered a choice to view and modify the existing program or delete it and start fresh. Let's delete it. We're asked to confirm our selection by pressing OK. We'll return to the previous screen. We can navigate to the Program entry using the arrow keys and press OK. We're offered a blank screen. This is where we'll write our program. Before we write a program, let's first discuss the programming format offered by the EZ512 Intelligent Relay. The small display allows a ladder logic diagram with 4 columns, 3 of which are input or contact fields on the left, and the 4th is an output or coil field on the right. A rung in a ladder logic diagram is intended to have 3 contacts wired to a coil. However, if you want to use less than 3, this option is available. We'll discuss rungs necessitating more than 3 contacts in later lectures. The EZ512 can run a program with up to 128 rungs in a ladder logic diagram. Available input or contact types include, but are not limited to, terminal inputs, cursor buttons, retentive markers, non-retentive markers, analog comparators, counters, timers, and software-generated output contacts. Terminal inputs are field inputs I1 to I8, and the cursor buttons are on the front of the device. These are real inputs that really interact with the real physical world. In contrast, the remaining contacts are software-generated virtual elements. Some of these available contacts have coil functions and customizable parameters. We'll discuss the significance of this when we examine these features in later lectures. For now, here's a brief overview. A marker, if you want to think of it this way, is the programmed equivalent of a virtual relay and its associated contacts. There are 16 retentive markers, meaning the state of the marker and its associated contacts are maintained at power off, and 16 non-retentive markers, meaning the state of the marker and its associated contacts are not maintained at power off. Comparators, counters, and timers obviously perform comparison, counting, and timing functions and can be used to coordinate the activity of a system. Software-generated output contacts are kind of like the programmed equivalent of an auxiliary contact. When an output coil changes states, these contacts also change states. Available output or coil types include, but are not limited to, contactors and negated contactors, set and reset coils, rising and falling edge coils, and impulse or toggle relays. For this particular lecture, we're only going to use terminal inputs and a traditional contactor coil. A contactor coil is equivalent to the output enable instruction. When this is set to logical 1, that output is energized. We'll discuss some of the other coil options in later lectures. Just look at all the cool toys you have crammed in this tiny reprogrammable device. If these were real physical elements rather than virtual programmed ones, imagine the size, weight, and cost this would entail. This flexibility is one of the principal advantages of programmable logic controllers. Add to this advantage the fact that the device can be reprogrammed and updated without tediously rewiring all the hardwired components. Returning to our blank screen, we can now enter our basic program. Let's program the toInput AND function by placing two make functions in series with one another. Let's use inputs I2 and I3, and we'll use it to light a pilot lamp on output Q1. Here's a general guideline to use the dedicated buttons in the front of a device to enter a program. Rule 1, never use the dedicated buttons on the front of a device to enter a program. They're ridiculously hard to use because of all the annoying proprietary shortcuts that change from manufacturer to manufacturer. It took me no small amount of patience to figure out how to toggle between the different coil options in the Easy Intelligent Relay family because I was using the shortcut used by a different manufacturer. As soon as I figured out how to do it, I forgot it. Additionally, the LCD screen is super small and hard to read in certain lighting conditions. Add to these annoyances, these devices are very easy to throw forcefully against a wall in moments of extreme frustration. Rule 1, never use the buttons on the front. Always write a program on a PC using the manufacturer-specific programming software and then transfer it to the device using the programming cable. If you've got this option available, use it. You'll be glad you did. This being said, our demo program is pretty simple, and you'll appreciate the ease and utility of the programming software that much more after being exposed to this unnecessarily complicated procedure. Long story short, arrows change your position on the screen. OK inserts something. One could then scroll through the options using the arrow, and then OK will select it. Alternate inserts a wire or changes the logical nature of an instruction. Delete deletes something. Once you've entered a program, press Escape to back up and save it. And away we go. Press OK. The device inserts contact I1 as a make function. If I wanted to change this to a break function, I'd have to press alternate. The EZ512 indicates a break function with an overbar. I can press up or down to scroll through the available contact options. Once you've got whatever contact function you want, now choose which contact you want by scrolling up and down through the numbers. We want input 2, so up arrow once until the display says I2. Press OK. The device inserts I2 and moves us one column to the right. If you dork something up, you can always delete it. Press OK to insert another contact. The device again inserts the default contact I1 as a make function. Then scroll up to 3. Press OK. The device inserts I3 and moves us one column to the right. Note the device has already connected I2 and I3. We're not going to be using the third contact column in our program since it only has two inputs. Press alternate to insert a line. Wiring is probably the most confusing part of programming any programmable logic controller using the front panel regardless of manufacturer. Again, if you dork something up, you can always delete it and try again. The cursor changes to a flashing arrow. Press the right arrow key. Now get out of line drawing mode by pressing Escape. You're now in the coil field. Press OK to insert a coil. Note the device inserts the default output coil Q1. Luckily, this is the one we want. If you wanted to, you could press the left arrow to back up, then scroll up or down to change the coil function. If you wanted to, you could stay right here and scroll up or down to change the coil to a marker or other program element. You can now choose which coil by scrolling up or down the numbers. Press OK to select Q1. The device inserts a Q1 and moves us to the second rung. We have successfully programmed this device. Press Escape, then save the program by pressing OK. Press Escape again to back up to the main menu. Before we place this PLC in run mode, let's take a look at our sample system again. Given our program uses only inputs 2 and 3, let's ignore the other devices and concentrate our attention only on those devices connected to inputs 2 and 3. Note the device attached to input 2 is normally closed by nature, despite it being instantiated in the PLC program as a make instruction. Remember, the electromechanical nature of a switch's deactivated state has absolutely nothing to do with how that input is logically instantiated in a PLC program. Recall that PLC programs require logical continuity, unlike traditional hardwire relay-based ladder logic that requires electrical continuity. In this case, our ladder logic program utilizes a make function for both input 2 and input 3 in series with one another to logically energize output coil Q1. Can you predict how this PLC program will respond to 4 different scenarios? First, when both the red push button and green push button are in their deactivated state. Second, when only the red push button is activated. Third, when only the green push button is activated. And finally, fourth, when both the red push button and green push button are activated. By all means, pause the lecture and think about this. Here's a hint. What logical values do the red and green push button respectively send in their deactivated and activated states? And how do these logical values affect operation of the program? Let's run this program and see how the PLC responds to these 4 different scenarios. Navigate to stop run and press OK to place the program in run mode. Navigate back to the intro screen. When neither button is activated, the PLC indicates only I2 is receiving a logical 1. No output coil is energized. When only the red push button is activated, the PLC indicates no input is receiving a logical 1. No output coil is energized. When only the green push button is activated, the PLC indicates I2 and I3 are receiving a logical 1. Output coil Q1 is energized and the pilot lamp comes on. Note there's an audible click when the electromechanical relay Q1 closes. When both the red and green push button are simultaneously activated, the PLC indicates only I3 is receiving a logical 1. No output coil is energized. This behavior makes perfect sense. When both buttons are in their deactivated state, the normally closed red push button sends a logical 1 to input 2, and the normally open green push button sends a logical 0 to input 3. There is no logical continuity to energize output coil Q1, and the output remains de-energized. When only the red push button is activated, the now open red push button sends a logical 0 to I2, and the normally open green push button sends a logical 0 to I3. There is no logical continuity to energize output coil Q1, and the output remains de-energized. When only the green push button is activated, the normally closed red push button sends a logical 1 to I2, and the now closed green push button sends a logical 1 to I3. There is now logical continuity to energize output coil Q1. The electromechanical relay would close, and the pilot lamp would come on. The relay, being electromechanical in nature, would exhibit a characteristic audible click when it closed. Finally, when both the red and green push button are activated, the now open red push button sends a logical 0 to I2, and the now closed green push button sends a logical 1 to I3. There is no logical continuity to energize output coil Q1, and the output remains de-energized. Something called the power flow display, offered by the EZ512 Intelligent Relay, confirms our observations about logical continuity. To navigate to the power flow display, the PLC must have a valid program stored and be in run mode. Rather than being a means of programming a stopped device, from the main menu, the program entry now shows the state of the inputs and outputs as manipulated by the operational program stored in memory. When no button is being activated, the power flow display shows I2 is allowing logical continuity to I3, symbolized by a highlighted bold rung. However, I3 does not pass the logical connection out to the output. The output remains de-energized. When only the red push button is being activated, the power flow display shows no input is allowing logical continuity. The output remains de-energized. When only the green push button is being activated, the power flow display shows I2 is allowing logical continuity to I3, and I3 is allowing logical continuity onto Q1 output, symbolized by a highlighted bold rung. The output is energized and the pilot lamp comes on. The output, being electromechanical in nature, would exhibit a characteristic audible click when it closed. When both the red and green push button are being activated, the power flow display shows I2 is not allowing logical continuity onto I3, and I3 passes on a whole lot of zeros to the Q1 output, and the output remains de-energized. Here's an actual system performing this same program. We'll learn to make this inexpensive PLC trainer in later applications exercises. Note when no button is being activated, the output remains de-energized and the first pilot lamp is off. When only the red push button is being activated, the output remains de-energized and the first pilot lamp is off. When only the green push button is being activated, the output is energized and the first pilot lamp comes on. When both the red and green push button are being activated, the output remains de-energized and the first pilot lamp is off. If you consider yourself up to the task, I leave it as an exercise to the viewer the following 2 challenges. Challenge 1. Given the system is wired as indicated, how would it respond if programmed using the following ladder logic diagram for all possible combinations of input? Note, for this implementation, I2 has been instantiated as a break instruction in series with I3. Again, recall that the electromechanical nature of a switch's deactivated state has absolutely nothing to do with how that input is logically instantiated in a PLC program. Put your thinking cap on and figure out how the make and break functions respectively respond to the deactivated and activated states of the associated input devices. Think beyond colors. Red doesn't necessarily mean stop anymore. If you've got a PLC available, program it and see if your expectations match reality. Here's a quick programming hint. To change between the make and break logical operation of a contact in a program, one would press alternate. Challenge 2. Again, given the system is wired as indicated, predict how it would respond if programmed using the following ladder logic diagram for all possible combinations of input. Note, for this implementation, I2 is not in series with I3, but rather in parallel. If you've got a PLC available, program it and see if your expectations match reality. Here's a quick programming hint. To add wires, press alternate, then use the arrows to draw wires. Press escape to get out of wire drawing mode. Delete would delete wires or devices that aren't needed. Alright, this about wraps up our brief introduction to the Eaton Easy Intelligent Relay, just one of the many different types of basic fixed programmable logic controllers commercially available. We familiarized ourselves with the layout and specifications of an Eaton Easy 512 DCR Intelligent Relay and learned to navigate the menu and program it using the dedicated buttons, annoying proprietary keystrokes, and the ridiculously small LCD screen. We'll be taking a look at the much easier to use EasySoft programming software in later lectures. Additionally, we monitored the status of inputs and outputs using the status display and verified the function of an operational program using the PowerFlow display. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.